So today we start our transition into the realm of statistics known as inferential statistics. But before we do that, let's talk about where we've come from. So in Unit 1, we looked at what is known as descriptive statistics, that is, methods of describing data. So first we learned about how to properly gather data, with the gold standard being simple random sampling. Then we looked at different ways of describing or summarizing the data either numerically or graphically. From there, we then went into the unit that we've just completed, which is the interlude unit, in which we looked at some basic principles of probability and introduced the idea of a probability distribution. And then we looked at two key probability distributions. The first one being what is known as the normal distribution, which is an example of a continuous probability distribution. And then we looked at another one called the binomial distribution, which is an example of a discrete probability distribution. Those two distributions were looked at in Chapter 4 because they're going to carry us. We're going to use those two as the foundation for everything we talk about in the unit that we are now going into, inferential statistics, which will be units 3 and 4 of the course, in which we now are going to use all of the machinery we've developed to learn how to answer questions from data. We call that torturing the data. And that will be chapters 5 through 8 from our textbook. So before we go into talking about our first topic in inferential statistics, I just want to go ahead and highlight the fact that throughout the rest of the course, you're expected to use appropriate notation for each of these key numerical quantities that are on the left-hand side. So the mean, standard deviation, variance, proportion, and median. When we write notation for any of those 5 numerical quantities, when we're talking about a population, the term used for those is parameters. And you can see in the chart that we use Greek letters for each of those, with the only exception being the median, which has no special notation when it's for the population parameter. On the far right, we see the notation that you need to use when you're talking about those 5 numerical quantities in the context of a sample. That is the statistics. We have x bar, lowercase s squared, lowercase p with a hat over it, respectively, for the mean, standard deviation, variance, and proportion. And then the median has x with a tilde over it for representing that notationally. Now that we've discussed key notation for the mean, standard deviation, variance, proportion, and median, let's take a look at some key thoughts that are going to guide us going forward. We're often interested in finding a population parameter. For example, suppose I want to know the percentage of U.S. voters who voted for a particular candidate for president. Now, getting an answer to that question is going to be very difficult if I'm going to try and gather that information from the entire population of all U.S. adults that voted. In fact, that's going to be almost impossible to collect data from everybody. Therefore, we're forced to consider using sample statistics as a way of trying to get an answer to the question I asked. And those will be used as a point estimate for the unknown population parameter of interest. In this case, the proportion of voters that voted for a particular candidate. So here's the key question, and this is an important question to answer, because if we can't answer this question in a positive way, then the whole process of statistics goes out the window. How do we know that sample statistics will adequately estimate population parameters? Because if they don't, then we're wasting our time in this course. And so that's what we're going to take a look at, is how we can start to know that using sample statistics is a way of estimating population parameters. So to start answering that key question we saw in the prior slide, let's look at the following scenario. Suppose that we have a population that consists only of the numbers 2, 3, and 7, and we're going to assume there's an equal number of each of those 3 numbers. It could be as simple as having just the 3 numbers on 3 slips of paper inside of a hat. We want to find the mean, the median, variance, and standard deviation for that population of numbers, and in addition, I want to find the population proportion of odd numbers. Well, fortunately, it turns out those are fairly easy to calculate. And I've gone ahead on this slide and shown how you can find the population mean, population median, population variance, and population standard deviation using formulas that we've covered back in Chapter 2 or using technology. And then also we see that finding the population proportion of odd numbers is very simple. There's only two odd numbers, the numbers 3 and 7, out of a total of 3 numbers, so the population proportion is just 2/3. So now that we've talked about how to find the 5 numerical values for the population, the mean, the median, proportion of odd numbers, variance, and standard deviation, let's start talking about those same 5 numerical values in the context of a sample. And this is going to get us into the area of what is known as sampling distribution. So we're going to randomly select samples of size 2 with replacement. So that means I pull a piece of paper out of the hat, put it back in before I draw the next piece of paper with the numbers 2, 3, and 7. Now notice that in this case, there are 9 different possible samples that could be drawn out of the hat. I'm going to show those on the next slide, along with each sample's corresponding statistics. So let's take a look at that slide. Here on the far left, we see the 9 possible samples that could be drawn, samples of size 2 that could be drawn from the hat, and then the corresponding sample mean, median, proportion, variance, and standard deviation corresponding to each sample. So for example, if I draw out a 3 followed by a 2 from the hat, the average value is 2.5. You add the two values, divide by 2. The median is exactly the same value, 2.5, because that's in between 2 and 3. The sample proportion is 1 out of 2 because there's one odd number out of the 2 numbers drawn. And then we can calculate the variance and standard deviation using a formula or technology. Okay, so that's the values, the sample statistics for all 9 of these samples in the table. So now that we have found these 5 sample statistics for all 9 samples shown in the table, let's talk about a way of presenting that information in a more usable fashion. So let's start first of all talking about what we call the sampling distribution of the sample means or medians. Notice in the table on the right, I've taken all the possible values that we found for the sample mean or median. I've listed those on the left, and I've counted how many of each of those values there are. Now, this particular distribution is known as the sampling distribution of the sample means or medians. Using technology, we can find the mean and standard deviation for this sampling distribution. We find that we get a value of 4. Now, here's the thing to notice. From the mean of the sampling distribution of sample means or medians, we see that this value of 4 matches the population mean of the original numbers 2, 3, and 7 that we had. However, this sampling distribution of sample medians mean value does not match the median we found for the population as a whole. And then here I've also shown the standard deviation for this distribution in this case. Now let's move on and take a look at the sampling distribution of the sample variances. Again, I've used the table that we had on the previous slides to count up how many of each of these sample variances there were in the table. I can again find a mean value for this sampling distribution of sample variances, and here's the notation for that, mu subscript s squared. And I see that the value is 14/3. Notice that that matches the variance of the original population. Okay, so keep that in the back of your mind, that that is the same as what we saw for the original population. So the mean value of the sampling distribution of sample variances does match the population variance that we found earlier. All right, let's take a look now at the sampling distribution of the standard deviation. So again, I've created a table where I counted up how many of each of the sample standard deviations there were in that table of 9 samples. I use technology to find the mean of this sampling distribution, and I get a value of 1 in 571 thousandths. That does not match the population standard deviation that we had found earlier. All right, and the last thing I want to take a look at in looking at a summary of all these different statistics that we had in the table of 9 samples, this is the sampling distribution of the sample proportions. What I mean by that is I went into that table of 9 samples that we saw earlier, counted up how many of each of the different proportion values there were, got this frequency table. Then I used some technology to find the mean value for this sampling distribution. I came up with a value of 2/3, which happens to match the population proportion of odd numbers that we saw earlier for the population. So here's what we have now found. In summary, we found that the means of the sampling distributions of sample means, sample variance, and sample proportions of odd numbers were exactly the same as the corresponding population parameters. And it turns out that that is true in general. Therefore, we say that the sample statistics of the mean, variance, and proportions target corresponding population parameters. However, we also found that the means of the sampling distributions of sample medians and sample standard deviations were not the same as the corresponding population parameters. And that turns out to be true in general also. Therefore, we say that the sample statistics of median and standard deviation do not target corresponding population parameters. Now you may be asking, so what? Well, let's go back to that key question that we had asked earlier. How do we know that sample statistics will adequately estimate population parameters, or for that matter, do they? We now have at least a partial answer. We think that sample means, variances, and proportions can serve as suitable estimators of the corresponding population parameters. Next time, we will focus our attention on the use of sample proportions as estimators of population proportions, and that's going to occupy our time in Chapter 5, is that particular focus.